Okay, welcome back, guys. Um, Today we're on to the beginning of 5.5. My thing has to calibrate. You're going wrong here. Come on. 1 second. Now, what does that mean right there? Oh, great. Okay, so today we're just going to do the beginning. Um, Integration in cylindrical coordinates. So let me just say, we've got a nice pace going for the course. There's not very much material left to cover. So I'm going to spend today doing cylindrical coordinates. We'll see how far we get. And hopefully you don't feel like it's too much information in a day. And then tomorrow we'll do spherical and send the same thing, and then we'll see where we are on Thursday. Okay, so we did sort of already see this. I think there was one problem I did where I just kind of jumped through and uh, used this technique, but um, yeah. So I'll do the recall like this. One second. In polar coordinates, we set up polar integrals where we have this region that's best described in polar coordinates. Looks kind of like this. And then our function took values over this shape. So maybe the function looks like this or something like that. And so we have a three-dimensional volume we're trying to find. And over any one of these regions here, we get a little shape. This is our basic element right here. This is the kind of shape that we're finding a whole ton of and doing a Riemann sum. We set up some Riemann sum to add up the volumes of a whole bunch of these things, and that becomes an approximation for the total shape. And we take, n larger and larger, we get more and more little pieces, and there's some kind of a convergence going on there. So cylindrical coordinates is a kind of 3D integral. So the region we're integrating over now itself has this kind of cylindrical symmetry to it. So maybe it's like this kind of thing. Maybe we have a shape like this. Let's go a little farther. Something like that. A little cylindrical sector. And we have these coordinates now, or we want to, let me say, just decompose. We want to decompose this shape. Come on. I'll just do like that, this, into a bunch of little pieces. So maybe here's one piece right here. Oh, actually, you know what? Let's go one step further. We can also decompose it vertically. So let's go like this, like this. So yeah, maybe like I'll do a different color. So one piece is like right here. But then our function, just like it was for Euclidean integration in a 3D, can be interpreted as some kind of a heat or density. It can be very hot or very dense in some regions and then less so in other regions. So it's not the same picture as cylindrical coordinates, but it's similar. So what are the ingredients that we have to integrate here? Well, as always, we need a function we're going to integrate. We need to sample it at some point. We have to talk about what these points are. And then we need a base to integrate over. So in this case, it's going to be a volume because it's a 3D integral. And cylindrical coordinates, what we're going to have is we have an r and a theta in the xy plane. But then in the third direction, we still just preserve the z. So we'll have an r, a theta, and a z. And the delta v, well, in the base, we've got this approximation of area that's represented by r, delta theta. And then we have a height, delta z. And how does this happen? And then altogether, we can call this something like maybe delta H, which is well, the total heat in that little region, or you could call it delta M, like the total mass in that region. These are just kind of to get your ideas cooking. Either way, if we give that region a name, we call it R, then as always, we can put meaning to the idea of the integral over R of the function f in cylindrical coordinates with respect to the volume by taking this limit where we are imagining we have decomposed our shape up in three directions. And in the little grid or set of coordinates that we make over this shape, we sample points. And for every 1 point we sample, we have some amount of volume there represented by R at that point, Ri, times the little delta R, delta theta, delta Z. And uh, if the region is given by, let's say, all R theta Z such that maybe R goes between A and B. Theta, we usually use Greek letters. Theta goes between alpha and beta. And then Z goes between C and D, let's say. Then this actually comes out to be an integral. We can write this in many orders, but let's go the one that I just put. So R, well, no, I want R on the inside. Let's take Z from C to D. Theta from alpha to beta. R from A to B. And now our integrand is not, oops, just F anymore. It picks up that same factor of R that you always see when you integrate with respect to some kind of polar coordinate system. And then this order is dr d theta dz. And then I'm just going to say real quick, um, Fubini's theorem again. And then there are five other orders. I don't want to write them all out. We've already seen this. But you can do dz, d theta, dr, d theta, dr, dz, whatever, all equal. Okay, let's just try to collect what we've seen there. So we're extending alternate coordinate systems to 3 dimensions. So far, the only new one we've got for 3D is what we're calling cylindrical coordinates. It's polar coordinates in the base, with the third coordinate being z. We leave that one alone. The only real math takeaway from all of this, like kind of theory that I just laid out, is the kind of concrete demonstration that we do in fact see that R come up again, that extra factor of R, that Jacobian factor of R come up again. And then just also that Fubini's theorem, as always, applies, and we can do any order of integration that we want. But just say one more thing that's kind of an aside, but it's a good aside for you to take note of, which is the following. It's just a few different examples of things um, expressed in Euclidean and polar coordinate. And we'll say Euclidean. This just means x, y, z, and not polar, but cylindrical. So some example shapes. So a circular cylinder. How do you express a circular cylinder in 3 dimensions? Well, it looks like a circle. This blows my mind that this keeps happening. It looks like a circle in the XY plane. Not Z, whoops. Right? For any, so if you look at x squared plus y squared equals c squared in the XY plane, you get a circle, but it doesn't depend on Z. So in 3 dimensions, this becomes a cylinder. And then we can write this way in cylindrical. There's no dependence on theta or Z, right? It's just a statement about R. Let's try another one. Let's say you wanted a cone. So what does a cone look like? Whoops. Oh, you terrible. So then maybe like this, right? Well, Z equals some constant C times the square root of x squared plus y squared, right? C is the slope of that cone there. Well, Z equals C times R is the same cone expressed in cylindrical coordinates. And let me just get through two more. I'll just try to do them quickly. Let's go this guy. Blue again. Sphere. That's a little oblong, but just go quickly through this. Uh, X squared plus Y squared plus Z squared equals C squared is a sphere in Euclidean coordinates. And then just R squared plus Z squared equals C squared is a sphere in cylindrical. And then the last one, I think, is a paraboloid. Yeah. So a paraboloid, Z squared equals whatever, some constant C squared times X squared plus Y squared. It's a circular paraboloid. Z squared equals C squared R squared. Or actually, they use a C, so I'll just use a C here. Yeah, we'll just use C R squared. And then this guy's like this, basically. Okay, sweet. So the point of all of that is just to say you want to reflect on how these kinds of different symmetries are expressed in cylindrical coordinates, right? Like a cylinder has a full rotational symmetry. So does a cone, a sphere, and a paraboloid. All of these things, if you rotate them around the z-axis, what you see is the same. It doesn't change, right? So that's what we mean by symmetry. And that kind of symmetry is expressed in the mathematics in cylindrical in the fact that there's no dependence on theta. All of these expressions are expressions in R and Z, of course, but there's no dependence on theta. And so when you see that, you can infer before you even see the image that there is going to be a circular symmetry. Okay, that's enough theory. Of course, I'm sure most students are more concerned with um, how to do examples. So let's try to get through a few nice, simple, clean examples. Then I'll send you guys on your way. Um, yeah, so here they give us a quote unquote cylindrical box, and it's given by all points are theta and z with the properties 0 to 2 for r, 0 to pi over 2 with theta, and then 0 to 4 for z. And they ask us to integrate the function z r sine of theta. Okay, so first things first, just to be entirely clear about the coordinates, if this is z, and we'll call this theta equals 0 over here, r goes from 0 to 2, so here's 0, here's 2. Theta goes from 0 to pi over 2, so we're in the first quadrant in the xy plane. So here's r going from 0 to 2, and theta going from 0 to pi over 2. And then z goes from 0 to 4. Boom. Yeah. Well, that's supposed to be a straight line, but that's the region we're integrating over. We can do any order we want. I don't see any one of them being particularly easy compared to the others. Let's go with dr on the inside and dz on the outside. Well, actually, let's mix it up. Let's do theta from 0 to pi over 2. Then r will go from 0 to 2. Z will go from 0 to 4. My integrand is z r sine theta. I never forget to put in that extra factor of r, that Jacobian factor. And I've set this up dz, dr, d theta. Okay, we're just doing math. If you integrate z, you get z squared over 2. We've already got a factor of r squared. This is from 0 to 4. Everything you see here is that innermost integral. If you plug in 0, you get nothing. If you plug in 4, you get 8. And 16 divided by 2. And we still have dr and d theta left to go. R squared goes to r cubed over 3. That there, whoops, is this guy. Plug in 0, again, you get nothing. Otherwise, you pick up another factor of 8. So now we're at 64 over 3. And I'm going to integrate sine of theta. Let's just get that in there. Negative, whoops, negative cosine theta from 0 pi over 2. If you plug in pi over 2, you get 0. Negatives flip, 64 over 3. Done. Okay, hopefully this is a little bit boring, right? In the sense that now you've seen a bunch of different kind of examples of these other kinds of integrations. So you just collect your thoughts and say, what do I need to remember? Well, it's cylindrical, so I put in another factor of r, and then I just kind of go. Let's try another example. Yeah. So I really do like the more geometric stuff. So they give us a region in this example. They just describe it to us. So E is the region E is given by these statements. Inside the cylinder, R equals 2 sine theta. So keep in mind, in polar coordinates, R equals 2 sine theta, that's a circle. And just like we saw previously today, if it doesn't depend on Z, then that extends to a cylinder in 3 dimensions. So we want to be inside of that cylinder, bounded, that's one thing, bounded below by the R theta plane, right? Which is the same as the XY plane. And lastly, they say, and above by the sphere with radius 4. And above by sphere of radius 4 centered at the origin. So I'm going to put in there above, whoops, by r squared plus z squared equals 16. We saw already that's the sphere in cylindrical coordinates. So they give us, and they just say set up. They don't want us to evaluate it. Set up an integral uh for a general function for a function f of r theta Z, set up an integral from over E. So I've said a bunch of times now, what we're learning is only setting these things up. Then at a certain point, you're just being trusted to do the calculation from that point on. So these problems start to become more and more like this, where they just say, look, just set it up because we know you can do the math beyond that, but do you have the geometric insight to set up the integral? Okay, so what do I need to see? I need to see this cylinder, r equals 2 sine theta. Let's try to draw this maybe over here. I'm going to put x over here and y over here. Or to put that another way, this is the same as I want to put, sorry, let me just put it the way I should have put it. I'll just put theta equals 0 over here. So this is like theta equals pi over 2. Okay, r equals 2 sine theta. The largest that gets to be is 2. So there's 2 right there. I see a circle in this direction. Okay. Going up. Oops, come on. Come on. We don't really have to go down, but I'm just going to leave it like this for now. So that right there is the cylinder. And we need to be inside this cylinder. Right away, you want to think that's the region really that I'm about to set this integral up over. Or let's say as far as the r and theta directions are concerned. So I'm going to want to find polar coordinates over this uh circle here. And then I'm going to want to extend them in the z direction. We'll get to that. So but you want to have at least kind of got this in the back of your mind. Okay, the next thing it tells us is bounded below by the r theta plane. So once again, with three-dimensional coordinates, once you've got two of the coordinates laid out, the third coordinate, in this case z, has to go between a lower function. Well, what is the lower function? This down here is all z equals 0, right? This is all z equals 0 right here. So that's my lower function. I'm bounded below by that. And then I'm bounded above by the circle of radius, sphere of radius 4. Can I get another color? So if this was 2, maybe 4 is like right there. So there's a sphere here. Right? And we are interested in the portion of that sphere that lies over this cylinder. So there's like a little no, I didn't draw that right, did I? Nope. Try again, Mike. I want that right there to be my top. So it should kind of be like this. There we go. Okay, so there's this piece of a sphere up top there. And we can write that this way, z equals root 16 minus r squared. And that's where I'm bounded above. So take a moment and reflect on that, right? I've got z navigating from some lower point to some upper point. Wherever I start in r and theta, z starts at 0. But where once you've chosen a place in R and theta to start, and Z starts going up, where Z ends depends on R. That's our ceiling. If you've gotten this far that makes sense to you, then you understand that we want an order where where Z is on the inside. And then we're kind of used to already from polar coordinates, R is going to be a function of theta. So we're going to do this order, R dz dr d theta. Now, let me just try to hit that even harder home. Let's go with one more color. This guy might do me good. I'm going to start at theta equals 0. Actually, no, I'm not pleased with that color. Sorry. Which one stands out best? This one, maybe? I'm going to start at theta equals 0. I want to paint this picture for you. So this is my outermost integral. Theta is going to go all the way to pi. So let's write that out. 0 to pi d theta. That's my outermost integral. And now, as theta takes this journey from 0 and it makes its way all the way over to pi, my next condition is on R. Maybe the darker one, yeah. Now let's imagine we're at some fixed theta. So maybe we're right here. This is our choice of theta here. R needs to go from the origin out to the blue circle's edge. What is that edge? It's 2 sine theta. So I'm going to take R now from 0 to 2 sine theta. This is dr. Now these things take a lot of space to write. Give me some more space, please. Boom. And now, last but not least, I'll use that same color again. If theta is on the way from 0 to pi and it stops somewhere, and R is on its way from 0 to 2 sine theta and it stops somewhere, freeze right there. We've got a theta value, we've got an R value. Now it's Z's turn to make its journey. And we've already seen Z has to start at 0 and end at 16 minus R squared. That's dz. We never forget to put in that factor of R. And then, well, we don't really know what function they want us to integrate. We're just saying, if you gave me a function f of R, theta, and z, I would put it right there. So because they only asked us to set up, this is correct. This is the final product. Excuse me. So I mean, I have a hard time convincing students to take my recommendations for how to think about these things. I strongly recommend you do this little story in your head. Like theta is on a journey. It's making its way from, 0 to pi. And that's what this outer instruction tells you, 0 to pi here. But every single step of the way along its journey, it has to pause and let R take its journey. That's the next integral, the next innermost integral. So theta is on its journey and it stops at every single step along the way and lets R take its journey. Well, r has to go from 0 to 2 sine theta. That's instructed here. So then you imagine that taking place. But just like theta has to stop and wait, now r has to stop and wait at every point on its journey, right? So that this innermost integral z can also take place. So for every single step on r's journey, z has to do something, and that's given by this innermost bound. And then go back and imagine theta takes a step forward, or well, actually, I would imagine it this way first. R takes a step forward, z goes again. R takes a step forward, z goes again until R reaches its destination. But then theta takes a step forward and it repeats. A little step forward in theta, R goes to 0 and takes a step forward, z does its whole journey. R steps forward, z does its whole journey. R steps forward, z does its whole journey, all the way to that new end. Then you go back to theta and step forward again. That's what's happening. That is the iterated process that we're describing. Can I do one more? Let's try to do one more and we'll call it quits. They ask us to do this one in two ways. So again, they give us a region E. Whoops, I've written EX so many times. What is E is bounded below by Z equals, yeah, so the cone Z equals root X squared plus Y squared. Above by the paraboloid, Z equals 2. Yeah, minus X squared minus Y squared. And that's all we need because these two guys actually intersect each other. So that actually creates a total like a, a floor and a ceiling, with no walls. It's gonna be a round floor and a round ceiling, but and they ask us to set up a triple integral to find the volume. So I'm gonna say set up an integral for the volume. That always just means integrate the function f equals 1. And they say in two ways. So in let's say the two they give us dz dr d theta and dr dz d theta, dz dr d theta, dr dz d theta. So this way and this way. Okay, let's see what we got here. Oh, we must conceive of the shape, must be able to reason about the shape. Good enough. Okay, this one doesn't really matter because it has no dependence on theta. Let's put theta equals 0 over here. And let's see if we can get this stuff right. So first, I've got a cone with slope 45 degrees. Let's mix up the colors. I've kind of nailed this one at 45 degrees. That's kind of unfortunate. Let's try to bend it a little bit. No, that's just really bad. All right. I mean, I guess maybe even steeper would make more sense. Yeah, let's pretend that's 45 degrees. Jeez. Sometimes, sometimes. Well, let's pretend that's 45 degrees. And this kind of goes on forever and ever and ever. I also have a downward facing paraboloid initiating at 2. Let's make the 2 like right here, maybe. Oops. Well, yeah, I'll take it. With my downward facing paraboloid, this goes on and on and on. Not like that really, but I just want to curve it a little bit more. There we go. Okay. So I haven't really rotated either of these in, yeah, I'm pissed at this drawing, but can I cheat and do like this? Boom. That's that direction, and then I've got one more direction. Yeah. Okay, so they intersect. I hope you can see this. They intersect along a circle. Below this circle, you see the cone. That's the bottom of our shape. Above this circle, you see a paraboloid. Now I'm going to cut away the extra because I think in this case it's really in, uh, instructive. So it looks like a top. I'm not sure if anybody knows what a top is. It's a little thing that kids play with where you twist it and it spins around and around and around. Okay, so the top of this top is described by z equals 2 minus x squared minus y squared. Put that another way, that's a z, whoops, my blue. Z equals 2 minus, come on, z equals 2 minus r squared. And then the bottom is described by the cone, z equals r. And then the gold line is described by where they intersect. 2 minus r squared equals r, or r squared plus r minus 2 equals 0. R plus 2, r minus 1. That's the same thing. R squared minus r plus 2, yeah, minus 2. And so the positive root is given by r equals 1. So another way of writing that gold circle there is just r equals 1. Now they want us to set up an integral. Over this region, and you've got to be able to see that we want the same thing as we did in the last example where Z starts its journey at the floor, the magenta colored floor, and has to go up until the blue colored ceiling. When you see that the shape is best described that way, you know you want DZ on the inside. So lucky for us, they asked for that in the first example. So let's go for that. So let's see, can I make this compelling? Let's try the gold one again. I want that gold circle. So I'm going to take theta from 0 all the way around to 2 pi. That's the outermost. For any one fixed choice of theta, I only want to go as far as the blue circle of radius 1, right? I gotta go as far as z equals 1. Come on. Right, in any direction, we go as far as z equals 1. Do that. And not z, sorry, r. R equals 1, r equals 1, r equals 1. And then once I've done that, if I do what I just said, I get this nice circle in the r theta base. The floor, however, is not 0 in z. The floor for z is r. And the ceiling is 2 minus r squared. They want me to integrate the function 1. I never forget that factor of r, and I've set this up dz, dr, d theta. So that is one way of writing the volume of that top. And now we have to accept the challenge. Oh, this is actually going to be a ton of work of putting dz inside, outside of dr. Yeah, this is going to be a bunch of work. Let me try to make this real good. Let's see here. Let's try to just draw that top as best we can. Why is it that sometimes this thing, I can't find the straight angle? I don't get it. Sometimes it's so easy. Go with that. Go with that. Now let's try to pretend that we were just given that top. Let's do it all in one color. So we know nothing about this thing, right? We're just kind of like it's suspended in space, and we come along and we want to analyze it. Well, it's rotationally symmetric. So we're going to go ahead and start with theta going from 0 to 2 pi. D theta, that's our outside. Now here's the deal. For any one theta, right? Let's say we pick like this theta, like right here. This is our choice of theta. This slices the shape in the theta plane. So we get something that looks like this. Hopefully you guys can see that. That's inside of the theta plane. So we have cut the top in this theta plane. And we need to describe that shape in Z and R. We have two coordinates in this shape. We've got R going kind of this direction and Z going this direction. Z goes from 0 to 2. But there's a problem. The shape we're about to try to draw has corners there and there. And above that line that I just drew, the shape will be described by these bounds here coming from the paraboloid. But below that line, the bounds will be described by these two straight lines here coming from the cone. So what z value is that right there? Well, r, we already know r has to be 1. The radius of the circle is 1. And so then that z value is also z equals 1. It doesn't look like it from my drawing because I wasn't thinking about that when I tried to draw it. So here's what we're going to do. Inside of theta, we're going to take z from 0 to 1. And we're going to find some bounds on r. And we're going to add in another integral, z going from 1 to 2. Some different bounds on r. What should the bounds be for the 0 to 1 part? Well, if r is a function of z, this guy right here is negative z, and this guy right here is positive z. And then if r is between 0 and 2, oh, sorry, 1 and 2, then the lower bound on r is this guy here, and the upper bound is this guy here. And r is a function of z. Keep in mind that was a paraboloid, z equals 2 minus r squared. So r is a function, if so, just do this real quick on the side. Z equals 2 minus r squared. R equals plus minus the square root of 2 minus z. This one is a 2 here. R squared equals 2 minus z. R equals plus or minus root 2. Yeah. Okay, well, then those are our two bounds, right? For z less than d, yeah. Okay, root. So down here we get negative root 2 minus z, and then up here we get positive root 2 minus z. Okay, let's just look at those two for a second real quick. It is great and also a little bit intimidating maybe to reflect on just how different an expression for an integral can be when you change the orders of integration. In the first case here, we have it neatly, concisely described by one integral. Here we had to break it into two parts. Here there's no square root symbols anywhere. Here we got some square root symbols. You know, we really end up with very different looking expressions. If you want to understand every different expression, you have to think in terms of these pictures of what changes first. Like up here, first we vary theta, and then for a fixed theta, we vary r, and then for a fixed r, we vary z. Here, it's different, right? First, we move theta, and then z goes up and down. And then for any one fixed z value, like that little purple line there, then r needs to go and do its journey up and down, or left or right, or whatever. I mean, there's no substitute for practice, so please do practice. Please email me if there are any questions. Keep in mind that there are office hours, there is a TA, et cetera, et cetera, et cetera. And good luck with everything, guys.